Hello everyone. Happy Wednesday. Welcome to another Wormhole Educate session. Today we've got John, Max and Dirk from Asymmetric Research. So I'm just inviting them up to the stage, and as they get ready... Hi Max. All right, you guys can start whenever you're ready.
I'm working on sharing my screen.
All right.
Sounds good. So we are from Asymmetric Research. My name is John Sagal, and I'm joined by my colleagues Max and Dirk. We are going to present to you today a presentation, how to write secure multi-chain apps, in particular using Wormhole. So the structure of our presentation is going to be split into 3 parts. We're each going to take one part. I'm going to begin. I'll start with talking about an overview of Wormhole. If you've seen other presentations in the series, you're probably already a little bit familiar with Wormhole, but we'll go over, again, some core concepts that are going to be useful for what we're talking about today. And following that, I'll talk about VAAs, which stand for Verified Action Approvals. They're a data structure that is used for writing multi-chain apps. Following that, Dirk is going to take over for the second part of the presentation, talking about how to actually use VAAs using examples of Solidity code, although the concepts we're going to talk about are actually applicable to other smart contract languages as well, Solana, for example. And he's going to give examples of using the general message passing bridge, which we'll talk about a little bit more and define, as well as the token bridge, which is probably what people are most familiar with about Wormhole. Finally, in the third part, Max is going to talk about security best practices. So not only how to do the kind of happy path development of using VAAs, but using them correctly and making sure that your application works in a secure way. And finally, after that, we'll take some questions if people have some. So let's begin. What is Wormhole? So I have a quote here from the documentation linked over there. Wormhole is a generic message passing protocol that enables communication between blockchains. So you have several disparate blockchain ecosystems that were never programmed to work together, right? This is a way to make them communicate and have some interoperability. The way that this is done is by using what we call a guardian. A guardian is a collection of full nodes for many different chains, as well as off-chain components. The off-chain components observe messages on supported chains, so any pair that, that is enabled on Wormhole. They then verify the messages that they receive, just making sure that they're well formed, and they sign them independently to attest that this is good information that we want the system to process. We require that a supermajority of the guardians sign in this way, and in so doing, they create a VAA, or a verified action approval. When I say supermajority, that actually means exactly at 13 of 19 signatures or more, representing 2/3 of the Guardian set. And if you want more information about that, again, check that link. There's a lot more detail into what a Guardian actually is. Wormhole is not a bridge. I feel like this is people know Wormhole as being a bridge. That is one of the main functionalities that Wormhole can perform, but it's not a bridge. It is a generic message passing protocol. So let's maybe drill down a little bit into what that means and why it matters for you. So I think a way that can be helpful to understand this is with reference to the OSI model. If you have some computer science education or experience with networking or other domains of programming, this is maybe something you've come across before. So when you speak to someone who is not a programmer, they might joke to you and ask how the zeros and ones are going, that you're just playing with all day, right? You're just shuffling them around. And they're kind of correct in a certain sense, right? Like that is the lowest level, most fundamental baseline of what we're doing, but we don't work at that level of zeros and ones. We have several layers of abstraction on top of that. So often we will think about bytes maybe as like a more abstract concept on top of the zeros and ones, or a way to interpret the zeros and ones. But we have many more layers on top of that. Instead of bytes, we might think about letters and numbers, and those are combined together to create messages. Messages are transmitted between different software processes or different hardware. And finally, we get to the level of where we can do like an Encode club presentation or Wormhole, right? That's like the highest level of abstraction we can get to in these systems. So when that comes to Wormhole, an analogy that is a bit more closely related to that might be something like TCP/IP in the networking layer, which is a way that computers can communicate. It's a protocol for connecting and disconnecting between hosts. But if you want to make a website, you will use HTTP, which corresponds to GET and POST requests, as well as several others. And that's built on top of TCP/IP, but again, it's a higher level abstraction. So let's bring this back to Wormhole now. So we can kind of think in loose terms about a Wormhole OSI kind of stack. At a lower layer is the Guardian peer-to-peer networking that we talked about before. Messages going back and forth, checking that they're well-formed, signing them, and reaching consensus when 2/3 of the Guardians agree that a message is good for some definition of good. Then we have VAAs, which is a layer on top of that. And even further, we have your application's data, your multi-chain app. And when we're talking about bridging, bridging goes at that highest level. It's built using VAAs, but this is why it's sort of incorrect to think of Wormhole as a bridge. It is a piece of software that can bridge via this more general message passing, often using VAAs. So let's get into what a VAA actually is. It's a term I've mentioned several times now. So again, this refers to a verified action approval. That is what the acronym stands for. And they're the core messaging primitive in Wormhole. This is essentially how we are like synthesizing the data passed between these chains that don't actually talk to each other. In a bit more detail, they are packets of cross-chain data emitted anytime a cross-chain application contract interacts with the core contract. So if you want to connect two nodes, you have your cross-chain application contract on each side, and they're facilitated by the core Wormhole contract and the guardians that are observing the events pass between these systems. Again, if you want more information, go to this link. So let's talk a little bit about this structure, what it looks like. Fundamentally, a VAA is a data structure. It's a way that we can encapsulate information and work with it. There are two like high-level subcomponents of that data structure that we're going to focus on. One is the header, and we're going to just talk about the header mostly because that's where the signatures are stored for the guardians that are signing this, reaching the supermajority to say that it's valid. And then the actual meat is in the body. And when you're writing a multi-chain app, you will be using the payload fields in particular, because this is where you are able to put your application's data in an arbitrary format to send and receive it on either side of a multi-chain app. So we can continue. So this is an excerpt again from the official documentation. It's good to review. So this is the VAA and specifically the header subcomponent that we were talking about before. And we're representing it here as like a Go data structure, or I guess it's a Rust data structure. I'm just looking at the types now. It doesn't matter. We have a few different fields in here. So what I want to draw the attention to mostly is the guardian set index and the signatures. The guardian set index is kind of like a snapshot of where the Wormhole guardians are at a time. So we have 19 guardians, but say one becomes inactive and another provider is swapped in. This is a way we can kind of encode that information, and we want to use the latest guardian set. We don't want to have old, out of date guardians being factored into new messages. This is just a sort of plumbing way that is incorporated. For the signatures here, we have a slice of signatures or an array of signatures, and a signature is the index corresponding to which guardian has signed a message. So in practice, this will be a number from 0 to 18, representing a 0 indexed array of the 19 guardians, as well as a signature of that message. So let's move on to the body now, because that's a bit more interesting. The body is where we can kind of get into some things that might be more clearly recognizable as a multi-chain component, something that we're interested in. Timestamp and nonce, number used once, probably a bit self-explanatory. We also see emitter chain. This is the chain from which a message was sent, and an emitter address, which refers most often to like a contract address. We need to consider these as two separate fields because in the EVM environment, for example, you may have a contract with the same address, but deployed on two different networks. So let's say Ethereum and Avalanche, they both use the same sort of addressing system. You want to be able to distinguish whether a message was emitted from Ethereum or emitted from Avalanche. As a note, I think the slides disappeared, Max. I'm not sure if you're seeing that as well.
Oh, really?
Yeah. So I can keep talking, but it'll be helpful to have the visual.
No, I don't know why. I said I didn't tell it to stop sharing. Sorry about that.
All good. All right, I think it's loading again.
All right.
Okay, no problem. We'll pick up where we left off. We also have a sequence field here and a consistency level. The consistency level is quite important and it's chain dependent. It relates to when a message is finalized on a blockchain network, and it's different between different blockchains based on their consensus model. For example, on Ethereum, there's a chance that when a block is produced, it can be sort of rolled back or not included in the canonical chain, whereas other chains have instant finality. So there's not this concept of like a block being made, being considered as the leader, and then dropped. And why we care about this is when we are sending, we're attempting to send a message from one chain to another, it's crucial that that message is not going to disappear later after we've used it. So we want to rely only on messages that we're very confident in that, will continue to be forward and that are safe to process on our network and on another blockchain. And then we're coming to the payload. The payload, again, is where the actual application-specific data will be found. And it's arbitrary bytes. It can encompass whatever your application needs. So Wormhole doesn't make it has like no opinion about what is put into this payload or the structure of it. That's something that you get to decide for your application's purposes. So that's the general overview. And while I've clarified that Wormhole is not a bridge, it is a generic message passing protocol, we are going to explore how the token bridge uses payloads in its multi-chain app, which is, again, the ability to bridge assets between chains. We're going to do this as an overview, and then we're going to talk about some other examples of multi-chain apps later in the presentation. In the token bridge, we have 3 payload types that we're most interested in. The first one is a token transfer, which is a relatively simple intention to send a token from one chain to another. The second type is an attestation, which registers a new token to be considered by the protocol. And finally, we have token and message, which is a custom payload that contains more detailed information about the application. And as a result, it can do some more sophisticated operations. Within the token bridge, there's also like a secret fourth payload, which if there is no payload type, it's considered a governance message. Anyway, for our purposes, we're going to focus on payload type 3 because it probably has more use and more application for what you might be developing. So let's get into this type of payload in particular, this payload type. Again, docs at the top. So payload ID 3 is being highlighted here just to, again, clarify that we're talking about a very specific kind of payload. in this section, we have some additional concepts that you might have noticed were lacking in the previous examples. So before we talked about the emitter chain, the emitter address. In this case, we also have here token address and token chain. This is the sort of like home chain of a token. We also have to and to chain. To is going to be a destination address, for example, and to chain again is like the destination. So why do we have token address and to chain as well as emitter chain? We're now talking about 3 chains, right? This is actually pretty important because when you send a message out from one chain, you may actually be dealing with an asset that itself was bridged earlier. So let's take the example of USDC coin that was minted on Solana, found its way to Ethereum, and now we're trying to transfer from Ethereum to Avalanche. In the VAA context, our emitter chain, since we're sending from Ethereum, will be Ethereum. The token address will be Solana because that's like the home chain where the asset was minted. And the to chain would be Avalanche because that's where we're sending. So those are some things to keep in mind and some ways to kind of distinguish and disambiguate those 2 fields. Within this payload, we actually have another payload. This payload is nested within the first, and this contains even more additional information that we might want to send as a message to accompany this token transfer. So we can encode additional application logic here, which will then be decoded, parsed, and used by the destination application in however way the developers have designed. So this is a recap of what we've just talked about in a slightly different view. I tried to encode the fields of the VAA almost as like a file tree that you might see on an operating system. So we can see the header that contains the signatures. We also have the body containing a bunch of different fields. And within the body, a payload and then an additional payload. So that's how a VAA might look. And if you were to go to a chain explorer using these, for example, if you go to Wormhole Scan, if you choose a transaction and go to the sort of detailed view of it, you will see this represented in JSON form, essentially. So I just wanted to provide this as a visual because we jumped around to a few different data structures and a few different contexts. So this is the way to think about it. And again, importantly, the data that you care about is going to be in the payload section. So this is coming to the end of my section of the presentation. I'll just give a few notes on notation to spare Dirk and Max the trouble. In the code examples you'll see, there's going to be this term VM. This is a historical term, and now we use VAA. So just try to do that substitution in your mind and don't trip over the notation. And secondly, an important thing to know is Wormhole has a concept of chain IDs that don't necessarily match with chain IDs as you might be familiar with them. So if you want to explore those, go to that link about the constants there. But it's just an important thing to know as you're working with Wormhole that when you see something as chain ID 1, it might not match with what you see in a chain explorer, for example. Okay, so that's it for me. Thanks. And I'm going to turn this over to Dirk now.
Amazing. Thanks, John. Yeah, so John's given a really good overview of like what VAAs look like internally. It's really important to understand that at a high level, at least, but as an application developer, you don't necessarily have to interact with all of those fields every time you're using an application. And a lot of that's abstracted away. So we'll start by looking at a few examples. So we'll start with generic message passing, and then we'll go on to token bridge. And I would say that there's a lot of things, or a few things in this presentation that you'll hear. You've heard John say, you'll hear me say, and then you'll hear Max say it as well. That's because it's really important. If we're all saying it, it's important, so make sure you remember those bits. Okay, so getting started. So let's start with just generic message passing. This is the bottom layer. This is Wormhole core. This is like how everything on Wormhole is built on top of this. And if we want to send a message, it's super easy, right? So a lot of these examples will have like a bit of a frame around them. So like the send message entry point, obviously your application will have its own entry point. that might be internal. You might have some other inputs to the application you might want. But you'll see inside that method, there is a wormhole.publish message call. And that is really as simple as it gets to publish a message cross-chain. And importantly, when you're publishing a message, you'll see that there are three inputs. So the first is the nonce, so nonce 0. The nonce is application specific on Wormhole. So Wormhole actually does have a sequence counter that increments per sender. So you're already guaranteed a unique message that you're not going to have a collision on. But if you want to do something like message ordering on the destination, you might want to explicitly use a nonce here. But for this example, we're using nonce 0. Then the second argument is the message. So that's the arbitrary bytes message that you want to send. So yeah, that's just any arbitrary byte array that's application specific. And then you have the consistency level that John mentioned at the start, which is how long do you want the guardians to wait before they will sign off on a VAA. And you'll notice here that send message takes these three inputs and passes them into to the wormhole publish message call. But as simple as this is, we've already made a few mistakes. So you might have already figured them out. But hopefully Max
there we go. This is what I wanted.
Next slide, please, Max. So yeah, the two mistakes with that really simple snippet is that we're letting the caller specify the wormhole address, and we were letting the caller specify the consistency level. And this is not a wormhole specific concept. This is just smart contracts in general. And the rule is basically don't let the caller specify data that they shouldn't be specifying, right? Try and minimize the amount of user inputs that your application takes. So here we've taken out the two inputs from the send message call outside, and now we still have the nonce 0. We have the message that the caller is passing in, and a finality of 1. So I should say consistency level of 1. So 1 corresponds to finality. So we wait for finality on the source chain that we're emitting from. So on Ethereum, finality is about 15 minutes, and we're telling the guardians to wait until the risk of a rollback is practically 0 before they sign off on a message. There is a constants reference in the Wormhole documentation that explains these consistency levels. So there's a few numbers, so 200 and 201 are not finality, and that means that guardians will sign before, while there's still a risk of a rollback. So for the most part, as an application developer, don't do that unless you really, really want to. And you need to have a very good reason for that. For almost everyone, you want to use finality, so consistency level 1. And something I forgot to mention on the last slide as well is you'll see we're passing in value into the publish message call. That's actually not needed at this time. Publishing messages via Wormhole is free. Besides the gas you pay, you don't have to pass any additional value in. But for future proofing, it's good to have this value call there in case the price does increase from 0. So that's the sending side. Receiving a message is also super easy. So you'll see that we have a receive message wrapping method, and we take in an encoded message, which is an arbitrary byte array. That's the VAA that John was talking about. So the VAA we get back is a arbitrary byte array, and we get that VAA and we call parse and verify VM. So again, VM is VAA. You make that one call and you'll get back 3 outputs. So you'll get the VM, which is a struct split up into all the fields that John showed earlier. So it makes it really easy to access that data that's encoded in the VM. You get a valid Boolean, and you get a reason in case the Boolean is not valid. So this is something that I can't stress enough. Always check that the VM is valid or the VAA is valid. If that Boolean is false, you should never, ever, ever use the VAA. So make sure you're doing that check. And then you can do whatever you want with the payload at that point. So the payload that you passed in originally, your arbitrary message. But there's still something wrong with the snippet. Maybe next slide, Max. Thanks. So, well, it really depends on your use case. And I think something we want to stress as a team is that a valid VAA doesn't mean that it's safe for your app. And that's really important to stress. So there are lots of things that, or lots of restrictions you can add to a VAA, but these are restrictions that are very application specific. And something that I'll really stress about the generic message passing bridge is that it makes few assumptions about what the developer wants to do, which increases the security surface for developers and what they have to care about, but it massively increases the utility of Wormhole. It means you can really make really interesting applications with Wormhole because it doesn't assume what you're going to do as a developer. So some things you might care about as an application is that maybe you only want your message to be delivered once, but maybe you want your message to be delivered 10 times. Like Wormhole doesn't know that, and it doesn't want to assume that for the application developer. Maybe you only want messages that come from Ethereum, and you don't care about any other messages from any other chains. I think I forgot to mention that earlier, actually, is that Wormhole is multicast. So when you're sending a message, it could be delivered onto any chain. It doesn't have to be. And yeah, maybe you only care about messages that come from Bob, right? And you don't want messages from anyone else. But Wormhole doesn't know that, so it can't make that assumption at the generic message passing layer. So moving on to the token bridge. So like John mentioned, this is probably, as an application developer, what you're more likely to be using. You want to send value cross-chain, and there are two main entry points to transferring tokens from one chain to another. There are a couple of others like transfer ETH, which transfers native value, but for the most part, you're going to be wanting to transfer ERC20 tokens. So you have a transfer tokens method and you have a transfer tokens with payload method. So they sound kind of similar, but as an application developer, you practically always want to use transfer tokens with payload. So this is the just snippet from the code with the doc string above it. And you'll see that the doc string really calls out kind of what this is, and it's a contract control transfer. So as an application developer, you have a contract and you want to control what happens with this transfer. So this is probably what you want to use. And you'll notice there are a few differences to just transferring tokens. Is you get to pass an arbitrary payload. So this is something John touched on earlier. You can, as an application developer, put in an arbitrary payload that you can then use on the receiving chain. And really important is bullet point 2 there, is that only the recipient can redeem the transaction with this type of token transfer. And that's really important because if you're specifying an arbitrary payload, if anyone could redeem your transfer, even though the tokens would go to you, you would never process that payload. So by restricting who can redeem the token transfer on the destination, we ensure that the application can actually use the arbitrary payload that it needs to do some arbitrary logic after the fact. And then, yeah, number 3, you also get the message sender included in the payload. So next slide, please, Max. So yeah, that's the sending side. I'll show you another snippet later about how you would call that. But on the receiving side, it's practically the same as the arbitrary message passing, so the GMP bridge. But you'll notice we don't have to do the VAA, the Boolean validity check here. So that's actually done internally on the token bridge. But yeah, you get the encoded message, which is the VAA, and you pass in the VAA to this method, complete transfer of payload, and you get a payload back. So super easy, one call, and you've got a checked, so that VAA is checked. It is a valid VAA, and you've got a payload that you want to do something with. So here, what security checks do we get for free now? So this is the difference between the token bridge and the generic message passing bridge, is that we can now make a lot more assumptions about what the developer wants. So when before we didn't know which chains we want to send to because Wormhole is multicast, when we're transferring tokens, I know that I only want my tokens to go to a specific chain. I don't want to send tokens from Ethereum, but have it redeemable on Arbitrum, Polygon, and any other chain, because now I've minted tokens out of thin air. Similarly, I only want my VAA to be redeemable once. We don't want to replay the same transfer and end up tripling, quadrupling the funds we sent on the source chain. And like I mentioned on the last slide, we only want the contract that's consuming the tokens to be able to redeem the transfer, since we need to use the payload. But there's still some checks missing that we haven't got for free. So what are they? So a really important concept, and something you'll see in a lot of applications that use Wormhole, is a concept of peers. So you'll see there's a mapping there at the top, which is mapping chain ID, so a uint16, to the address of a peer. So here, let's kind of do the receiving tokens flow of getting a VAA, and what I need to do as an application to check that the payload I'm getting is trusted. So the first step is still the same. We call complete transfer of payload with the VAA. We get back an arbitrary byte array, which is the payload, which is the validated VAA. We then have another convenience method that we expose to developers, which is pass transfer with payload. So this is really nice because it gets the arbitrary bytes payload and it passes it and puts it into a struct for you. So the transfer with payload struct, and it has like all the fields that you will care about from a VAA and the bridge specific fields of the VAA. Then we were doing, so here I'll kind of jump back on the next slide to what the sending side will look like. But on the receiving side, you would then want to decode your arbitrary payload. So this is the developer provided payload, so pass payload.payload. And as the developer, I've put in some data into that arbitrary payload. And in this case, I've put in the source chain ID and the sender payload. So this is kind of a hacky example. You wouldn't want to do this in reality because there's a simpler way to get the source chain ID, and that's something that Max will show later. But just for the sake of argument, as a developer, I want to check something about the peer. So I encode the data into my payload, I decode it on the destination chain, and then I do a check with that data. So here, the check I'm doing in the last line of that method is that we're requiring that the address that we receive from corresponds to the address that is registered on the source chain. So that's how I know that as an application, the payload I'm getting has come from my application on the source chain, and not just some random person who sent like one way of US, or like one unit of USDC to my application with an arbitrary payload that actually unlocks a massive amount of tokens on the destination chain, right? So we just need to have that trust, those trust checks there. But really important, again, like highlighting this, is that we need to make sure that we control the payload on the source chain, to control the data that the user is providing and that we put on the payload. So in this case, if we look at the sending side of this transaction we're talking about, so let's imagine we wanted to send USDC to a recipient chain. So we have a send tokens method that takes in 3 arguments. So it's the chain ID that we want to send to, the amount, and an arbitrary message. We grab the USDC from the caller, we approve the token bridge to take that USDC, And in the second half, we make a single call to the token bridge, and we specify the USDC, so the token we want to send, the amount, the chain ID that we want to send to. And here we have the same peer lookup. So on every chain your application is deployed to, you'll have a mapping, this peer mapping, that maps to every peer on all your other chains that you care about. So here we grab the peer of the recipient chain, so that's the destination address on that chain. The nonce, I believe, and then that's the nonce, right, Max?
I think you're right. I actually haven't really used the token bridge as much. I've only more so used the generic messaging layer.
Yes, it's the nonce. Yeah, so 0 is the nonce, and then the last field is the payload. So this is the arbitrary payload that the application can provide, and in this case, we're encoding into a single byte array the wormhole chain ID with the arbitrary message that someone wants to send. So this was what we decoded on the destination side, the chain ID and then the message. And you'll notice this is in related to what John said earlier. The chain ID for Wormhole is different to the EVM chain ID if you're on an EVM chain. So you can fetch the chain ID of the local chain by calling wormhole.chainid.
Hey, Dirk, can I add one thing here too?
Yeah, go for it.
So one thing that Dirk has here that works fine for EVM chains is we have the address set. We have this as an address type, but in the Wormhole ecosystem, addresses need to be 32 bytes because we support chains on other than EVM, such as Solana. I just thought it was worth calling that out in this case.
Yeah, definitely. Yeah, great shout. Yeah, so if your application, you only care about EVM chains and you know you're only going to deploy to EVM chains, you could stick with addresses and then just encode into 32 byte at sending time. But if you want to expand into other ecosystems, like Max said, you want to use 32 bytes to represent your addresses. Yeah, good call out, Max. Thanks.
Yeah, of course.
Okay, so this is the last slide for myself before we hand on to Max. And I think something I want to highlight is that depending on whether you're using the generic message passing bridge or the token bridge, you need to think about which checks you need to make depending on your application. And it's very application specific. So I would encourage you to think like an attacker. And this isn't Wormhole specific. This is just smart contract security. Just any smart contract you're building, try to think like an attacker. Secondly, better to have too many checks than too few. So we've seen a lot of cases of people trying to gas optimize on their cross-chain integrations. And this is not the place to be gas optimizing. So I have an analogy from John. The full credit goes to John for this analogy. I'm probably going to butcher it, but anyway, it's basically like you go out of your way to save money on gas for your car, but to do that, you risk your car getting stolen, your house burning down, and your arm getting cut. So it's just not worth it. Just add the checks. And so, yeah, thank you, John, for that. And yeah, lastly, just write tons of tests. If you have state, I would really recommend stateful fuzzing. We've had a lot of success with stateful fuzzing, particularly if you have lots of entry points into your app that mutate the state. Would really encourage that. But yeah, people generally kind of skimp on testing. So I would encourage you to spend a lot of time there. So I have a hand over to Max, who's going to kind of dive into a few of these security concepts a bit more. But in the meantime, in the chat, if there's anything that's kind of caught your eye that would make it easy for you to build with Wormhole, let us know. We'll make a note and chat with the team. So with that said, over to you, Max.
Cool. Thanks, Dirk. Yeah, I think that was a good overview of VAAs and how to use them. Now we're going to talk about how to use them securely. A point we're really driving home right now is the difference between the flexibility and security aspects. Wormhole is a generic messaging bridge, And that's very different from a lot of other things. And it's very unopinionated about how you are going to do things. And this is great because you can do things you can't do on other bridges, such as when you send a message, you can have something get attested for by a wormhole prior to the consistency level actually being met. But if you do this incorrectly for your application, then it has security consequences. So there's this teetering between the flexibility and the security that's really important to consider. And a lot of the security aspects of Wormhole do fall on application-specific use cases as a result. But it is very flexible. So that's the trade-off here. So I'm going to be talking about various mechanisms that need to be added to applications depending on your use case in order to make it secure. But under the hood, Wormhole is secure. We spend a lot of time working on it and making sure that the core infrastructure is good, and you can't spoof the source chain, for instance. So the one thing that Dirk said that was really, really true was with parse and verify VM, you do need to check this Boolean. This Boolean is not being checked is one of the more common things we see not being done on cross-chain applications. And if you don't check this, then you can pass in an arbitrary VAA with arbitrary signatures and pass in arbitrary data. And at that point, your application's compromised because you were able to accept a data controlled by an attacker. But there's a lot more that goes to writing an application than just parsing and verifying the VAA. And that's where the application-specific stuff starts at. So the first one we think about is replay protection. But I think it's good to think about this as a particular type of application. So the example I'm going to use for the rest of this presentation is going to be around a cross-chain oracle. We have the price of a token on one chain that's being used, and we want to update that price on other chains. So cross-chain oracle update. And on this, we're going to be receiving this cross-chain oracle update from a different chain. And so we're going to have a VAA that's being received on that. And this VAA should only be accepted once in this case. That's not the case in all applications, but in the case of a cross-chain oracle, we really only should be accepting this once, because otherwise I could take that same VAA sometime in the future and get it accepted. And that'd be really bad if the price was actually $10 and I was able to set the price to be $5 at some point in the future. That would be very bad to be able to replay this. So how do we actually fix this? The way we fix this is that the VM object has a field called hash. And we want to make a mapping from the hash to a Boolean so that when we receive the message, we can check to see if we've seen this before. So here we're checking to see if it's false. If it's false, that's the default value. We haven't seen it before. And then we set it to true. So the next time around, if we see this value and it's set to true, we know that we've seen this. And at that point, we know that some attacker is resending this VAA and that we should not accept this. So replay protection is something that most applications are probably going to want. The next couple have to do with the identity of who is sending the message and where it's going to. Dirk mentioned this as well, where we have peers. And the peer is who this is coming from on another chain. In the case of the cross-chain oracle example, it would be really bad if an arbitrary attacker or arbitrary address would be able to update our price. So we want to make sure that this comes from a known and trusted location. In this case, we have chain 1 and address AAA, and this is our peer from chain 1 that we care about. And we don't want an arbitrary address from chain 1, such as address X, to be able to set that. And again, this is application specific, but with the cross-chain oracle, we really only want a particular address to be able to set this. So how do we fix this? Within the Wormhole VM, we have the emitter chain ID, which is going to be the Wormhole chain ID. And then we have the emitter address, which is going to be a bytes 32. But if you're only dealing with EVM things, you can convert this back to the normal EVM address type. So the way that we tend to do this in our applications, such as with the token bridge, which also has to input this functionality, is you'd want to have this chain ID map to a bytes 32. And you'd set this as an administrator, either at deployment or have some sort of function to be able to set this. And once we receive this message, we can check to see if the expected address is what the emitter actually was. And if it wasn't, then we know this was sent from invalid location.
Max, can I quickly just comment on this?
Yeah, 100%.
Yeah, I just wanted to highlight that I mentioned in my slide that my peer check was already done way of doing it. So this is the way you should do it. So you'll notice the VM, so the VAA has the emitter chain ID encoded in it. So this is the chain ID that you should be using. You don't have to encode it in your payload as a user.
Yeah, 100%. Good call out. Thanks, Rick. So that's the peer aspect of, or where it's coming from. The next one is the destination. So if we look at the VAA, you'll notice that there actually isn't a destination. And this is a really cool feature of how Wormhole is designed. Wormhole is effectively multicast. And this means that we can make one VAA and send it out to multiple locations if we want. And an example of this is actually with our Wormhole governance. Wormhole governance messages have the ability to be multicast, meaning that I can send a VAA from one chain and they can go to all of the other chains, which means that I don't have to pay for as much gas, and the guardians don't have to work nearly as hard. So if you want to use the destination, then you're going to want to encode it in the bytes yourself. And as part of the payload that you're going to be making as the application developer. So if we go back to the same example with the cross-chain oracle, the cross-chain oracle actually would work really well being multicast, where I could write, when I wrote this on my initial chain and I emitted that VAA, the VAA could be used on all of the different chains, and now we actually know the price of that token. And this is a really cool feature. So instead of using the cross-chain oracle example for the to whom part, we're going to talk about a cross-chain bridge. And I'm not saying the Wormhole bridge. Say you wanted to create your own bridge. And we recently did this with like the NTT setup, or the native transfer tokens. So in that case, we only want to make sure that a single location is able to redeem that mint request. So the VAA going to should only be received by a particular destination chain with a particular address. If we could redeem a different VAA on the wrong chain, then we'd be able to mint the same token multiple times, which would be bad. So in code, the way we would do this is we would decode the payload coming from the VM, and there should be a ... here because this is included in the rest of the code that I was showing before. So once we've decoded the payload, and this can be arbitrary data, but we're always going to want to have an address, which could be, if you're on EVM, I just simplified, would be address. But if you're using something that was like on Algorand or SWI or something else, you'd want this to be bytes 32. And then the destination chain, which would be this. So here, we want to make sure that the destination address is going to match the address of this contract. And then we want to make sure that the destination chain matches this particular Wormhole chain ID. At that point, we know that this is only going to be received by this contract instead of the contracts on the other chains. So if we put this all together on the receiving side, we want to make sure that we're parsing the VAA from the Wormhole core, and we're validating the Boolean to make sure that this was parsed correctly. We want to make sure that this same VAA can only be redeemed once on this particular chain. And we do that by having a mapping from a bytes 32 to a Boolean. We also want to check the peer. And we do this by ensuring that an administrator who set the peer for a particular chain matches the emitter address for that chain. And then finally, we want to make sure that the destination address and destination chain match what we're currently on in order to make sure that this is redeemed once and once only. Another weird thing to consider is payload type confusion. Before, when we were talking about VAAs, we had the Oracle update payload, and that was it. But it's common for us to have multiple different types of payloads, such as when John was talking about the Wormhole token bridge having 3 different types of payloads. For our new example, we're going to have the Oracle update for payload 1 and then the vote payload for payload 2. In this case, they both use a UINT 256 where one is the price and one is the vote weight. You really want to make sure that you are checking the payload type. And this is because if you can use one payload in the wrong endpoint, then you may get some sort of type confusion. And in this example, the price of the token would be updated to 100, and that works fine. But what if we specified the vote payload and use that VAA instead? Well, now because we're not checking the application type, the vote weight being equal to 10, will now update the price to be lower than it actually should be, which is bad. So we want to make sure we check the types. And the way we do this in Wormhole is we have this transfer payload and the transfer with payload. And we have this payload ID at the beginning of each of these. And on the transfer, it's 1. And on the transfer with payload, it's 3. So in our application, if we had different entry points, we would make sure that only those entry points were receiving the particular payload ID, or you could have one generic entry point and just do your processing based upon the payload ID. On top of that, input validation is really important. If you're receiving data, make sure you only use trusted data from the VAA. There shouldn't be other fields that are being used. Like if you could specify the amount, like the token price, and that was outside the VAA, and you just specified that on the function call, that would be bad, of course. So input validation, input validation, input validation, think like an attacker. On the sending side, it's a lot simpler. Input validation on the payload, I think Dirk hit this hard enough. Just don't let users control too many fields. And the final one on the sending is the consistency level. For this, there are 3 different levels on Ethereum, but reading the documentation on this is important for each chain. The first one is finalized, and this means that there's virtually no chance of a reorg unless we have something like an Ethereum DAO sort of like reorg where we actually are intentionally reorging. Safe is fairly similar to finalized, but it's just a little bit more likely. I mean, in all likelihood, it's probably not going to happen, but still use finalized in most cases. And latest means that we are looking at the most recent block. And this seems crazy that you'd want to do this because there is a high chance for reorg, but there are cases where you'd actually want to use latest. And this is where the flexibility of Wormhole is really cool. If you wanted to build an application where you wanted to get users their tokens faster, for instance, then you could use latest for your thing. And you're thinking, Max, but it could roll back. And that's true. But in that case, you'd want to hedge your bet somehow and charge higher fees because the users want to get their tokens a little bit faster. But this flexibility is really cool. So from my end, that's all I have and all we have for today. We talked about how to use VAAs. We talked about what VAAs are, and we talked about how to use VAAs securely. At this point, we have we can answer questions from any of the sections or just Wormhole specific questions. So thanks everyone for attending.
Yeah, thanks everybody. There are a couple of questions that we saw in chat from a while ago, and I'll read them out just in the off chance someone is listening to this and isn't reading the chat. So Jumaru asked, can you elaborate a bit about the finality time? Should we consider that our app will always need about 15 minutes for a transfer? Anyone feel like taking that one?
I can take it, yeah. So, so like Max mentioned right at the end, if this is the case, if you're using finality for your application, but finality depends on the chain that you're on. So like Ariane mentioned there in the chat, the 15 minutes there is in the context of Ethereum finality. But if you're on a fast finality chain like Solana, I don't know how fast it is, but it's pretty fast. A couple of seconds, I think, right? The time you have to wait for the guardians to sign off on a finalized block is only a few seconds. So that's just in the context of the chain you're sending from.
And to be clear, not every EVM chain is going to be 15 minutes. Like I think is Optimism like really, really fast. I don't remember off the top of my head which one.
Yeah, Ethereum's the slower, so everything will be faster than 15 minutes. The longest you'll have to wait is 15 from Ethereum.
Yeah, there are some subtleties with that too, right? Because we showed Solidity examples and we think usually Ethereum or L2s, but there are also EVM compatible chains using other consensus mechanisms. So one of the things we support is Evmos, which is kind of bundled with the Cosmos system. There's Binance Smart Chain. There's these other things that have different finality constraints that can be faster because they have different consensus going on under the hood. Next question from earlier is from Jessica, who asks, can sender and recipient chain be the same chain?
The question is, it depends. It depends between the EVM implementation and non-EVM implementations. We've arbitrarily set different restrictions there, but I would say that you would never want to send to the same chain that you want to receive on. So when you're doing your peers, the peer mappings, don't register the same chain that you're on, like leave that unregistered. When you're sending to a recipient chain, make sure you have a check that the recipient chain, that if the user can provide that data, make sure it's not the chain you're on. I would add that in the application just to be safe, and don't try it because there are edge cases where you might do something bad.
It might also defeat the purpose of creating a multi-chain app, just to throw that out there. Yeah.
That was a really funny question. I feel like we realized that ourselves recently when we were auditing some Solana code.
Yeah. So we have a couple more minutes. Oh, sorry.
Yeah, I'm just checking through. I think all of the questions have been answered. Jumaru has just made a great point and said that this will definitely be a presentation that they'll rewatch a couple of times because it's gold, which I was going to say the same thing. You guys have explained everything so clearly. You've answered everyone's questions so well. I'm surprised anyone had questions because I feel like you explained everything so concisely and so clearly. So, amazing. We've got a couple of minutes left. If anyone has anything else they want to ask really quickly, otherwise.
Yeah, that was correct. So if finality is the source chain that you're sending from, so the guardians wait for finality on the source. They don't have to care about the finality of the destination chain.
Yeah, and again, a niche application here that Max did mention is you don't have to wait for things to be finalized. I would say in 99.99% of cases, that is the safe way to do it, but it's not enforced. You can do things with the rollback risk if you choose to. That's up to you. Wormhole doesn't necessarily enforce that.
Okay, I don't think we have any more questions. So I think if everyone can just say thanks in the chat for such an amazing presentation. I'm sure you've all, from the comments as we've gone along, everyone has clearly really enjoyed it. But thank you so much, guys. Yeah, have a nice afternoon/evening/morning wherever you guys are.
Thanks, you too. And thanks everybody for your attention and time. Yeah.
Thanks everyone.
Bye.
Cheers.